Let's go over Sn2 reactions. Now, just from the word Sn2, this is a substitution, a nucleophilic second order reaction. And so when you have got an alkyl halide, for example, instead of having ammonia, we remove one hydrogen. We have now CH3, and then we can put any halogen, for example, a bromine. So what you formed here is now an alkyl halide. For the alkyl group, we can just represent R. For any halogen, we represent X. So this will represent an alkyl halide. And so what happens is that for these alkyl halides, when they get to react with nucleophiles are simply substances which have got a lone pair of electrons which they are able to share with alkyl halides, or which are able to attack the alkyl halide to substitute the halogen. So let's say we have got this nucleophile and then we have got the alkyl halide here. So the reaction that gets to happen is that this is going to attack the alkyl halide. The bond here is going to be broken. The 2 electron goes on the halogen. And so at the end, we are going to have the nucleophile attached to the alkyl group. And then we are going to have the halogen now alone. So the halogen is called the leaving group. And then this one, which is attacked, is called the substrate. And so this is a simple example of an Sn2 reaction. So it only involves simple stage where the nucleophile gets to attack the alkyl halide. Now the nucleophile is always going to attack the alkyl halide 180 degrees from where the halogen is, meaning that there's no way the nucleophile is going to attack this substance in this direction, because that is where the halogen is. So because of this, the stoichiometry of the product is going to be inverted. So if the reactant alkyl halide was an S, let's say it was an S isomer, then the product is going to be R isomer. We are going to understand how those come about and how we get to show those reactions. Now, just from the reaction which I wrote earlier, we have got Rx reacting with a nucleophile, and this is going to us over product. So we can write the rate law because we know that this is a second order reaction, Sn2. So the rate law expression is therefore going to be K, the concentration of the alkyl halide multiplied by the concentration of the nucleophile. So what gets to happen is that the rate of this reaction depends on the concentration of both reactants. So when I quadruple the concentration of the alkyl halide, then I double the concentration of the nucleophile, then the rate is going to increase by a factor of 8. When I get to, let's say, triple the concentration of the nucleophile, I also triple the concentration of the alkyl halide, the rate is going to increase by a factor of 9. So that is why this is an Sn2 reaction, or a second order reaction. So the molecularity of this reaction, it is bimolecular or bimolecular. That is second order. Alright, so that is something that we need to get to understand. So we can have an example of how this reaction gets to happen. So it is a very simple reaction that gets to happen. Let's say, for example, I've got an hydroxide. Of course, we know that this oxygen has got 3 lone pairs of electrons. Because of that, it carries a negative charge. Let's say this one gets to react with this compound. So this is a compound that this is a nucleophile because it has got lone pairs of electrons that it is able to attack with this compound which is here. So what is going to happen now? We first need to identify or know the kind of stoichiometry for this reactant. We should also be able to identify the name of this compound. How many carbons are there? I've got 1, I've got 2, we have got 3, we have got 4. And we can see that at position number 2 we have got a bromine. So we can say this is 2-bromobutane. Now we also need to identify the stoichiometry of this compound. So when we want to identify the stoichiometry of the compound, what we are get to do is we need to know the priority order of some groups when we are determining the stoichiometry. And how do you get to know that? So we'll just get to check on our periodic tables. So if you consider this, on the periodic table we've got hydrogen, we have got carbon down, nitrogen, oxygen, fluorine, we have got chlorine, we have got bromine down, we have got iodine, we have got of course sulfur, we have got phosphorus, and these other substances. So as you get to go in this direction, the priority order of this group is increasing, and then as you get to go down, the priority order is also increasing, meaning that where you have got an iodine and a bromine in the same compound, you need to know which one is going to be more prioritized. Then you are going to give priority to the iodine. Right now, and hydrogen is the least of those you can give priority to. So again, the greater the molar mass of the compound, the more priority it has. Now for you to be able to give the direction whether it is going to be R or S, the R or S configuration, what you do is the first thing you need to find which of these 4 groups is the least important. So in this case we can see we have got a bromine, Fu, methyl, hydrogen. Definitely bromine is going to be the highest priority, and then you go now to alkyl groups. Considering their molar mass, that would tell you the priority. So this is going to be the second priority because that's got a higher molar mass. This is going to be the third. This is going to be the fourth. Now what you do is that you need to make sure that the fourth group is in front. Right? So we get to make sure that the fourth group is actually not in front but in the back. Now from what we're able to see, this one from the stoichiometry, this one is in front. So what you get to do is that you connect these numbers. So position number 1 is here, position number 2 is here, position number 3 there. So you just connect the first 3. Make sure that this one is in front. Is in the back, right? So when something goes like this will mean that it's going right. So this is going to be the R configuration. When something is going like this is going to be called the S configuration. So just join the first 3 numbers. Making sure that the fourth group is in the back. Now because this one is not in the back, it is in the front. So this configuration was supposed to be an R configuration, but because this group is in front, we change. So when the fourth group is in front, instead of this being giving you R, it is going to give you S. So meaning that for this one, this is going to be S2-bromobutane. Now what is going to be the product of this reaction? So what happened is that the nucleophile is going to attack the alkyl halide 180 degrees from where the halogen is. And the product which is formed should always be an inversion. So if this is S, the product should be R. So we are going to have a carbon, then we are going to add the bromine first before the final product gets to be seen. What we are going to see is there's going to be a partial bond formed with this one, and this bond is going to be partially broken before the final product. So we are going to see something like this. We are going to see the HO partially bonded to the carbon, and then this one is also partially bonded to the bromine, and then the rest are still there. So because there is a partial bond this side and there is a partial bond this side, we can see that carbon has got more than enough bonds. So it's going to have a partial positive charge, the carbon on the middle. because the bond is not yet broken, right? There is a partial bond here yet breaking, and then there's a partial bond here yet forming. And then from here, now we can have the product. Now this bond is going to be broken, and then the other one is now going to be fully formed. Now, as we have said, the stoichiometry of these compounds is supposed to change. So what you are going to see is that instead of this one being here and this one being here, I'm going to swap them. So I'm going to put this here, CH3, and then the hydrogen, I'm going to put it here. That is going to be H. We can see if the stoichiometry has changed. So in this case, oxygen has got more priority. So this is going to be position number 1. This is going to be position number 2. This is going to be position number 3. The position number 4 is supposed to be in the back, but remember that one is not in the back. So join these numbers 1, 2 to 3. So it has gone like this. This was supposed to give us S if this group was in the back, but it is in front, meaning that this is going to be R configuration. So this is going to be R. Now this is carbon number 1, this is number 2, this is number 3, this is number 4. So at carbon number 2 we have got an alcohol functional group. So the name for this compound is going to be R. Okay, at position number 2 we have got the alcohol functional group. So that will be R2. There are 4 carbons, butanol. So that is going to be the name, or we can say R butan 2O. So that is going to be the product that is formed in this reaction. So for an Sn2 reaction, it only involves one stage, and so if we want to see an energy diagram for this one, we have got energy and then we have got the reaction progress this side. We are going to see the reaction just going like that, and then it comes down here. Here we are going to have the product, which is R bonded to the nucleophile and the halogen, and then here we have got R bonded to the halogen plus the nucleophile. Here this is the transition state, which is the middle one, which we are able to see where we've got a bond partially being formed and the bond that is partially broken. Actually here I gave a positive charge. It's not supposed to be positive. We can calculate actually that charge. That's a formal charge. Formal charge is given by the valence electron. Carbon is in group 4, so it means it has got 4 electrons in the outermost shell, minus how many electrons are in this bond. So I've got 1 bond, 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons, so minus 5. This is going to give us negative 1. So this is supposed to have a negative charge here, not positive, right? So this is basically the mechanism for an Sn2 reaction. Now, what are some of the factors that get to affect the rate of an Sn2 reaction? Some factors that get to affect that. So one important thing that affects the rate of an Sn2 reaction is called the steric factor or the steric effect. So steric effect, if we with this property, when you want to maximize the rate of the reaction, the substrate must be unhindered. So steric effect is just talking about the hindrance that the substrate has. Remember, the substrate is simply the alkyl halide, so that hindrance that it is experiencing. So when you have got a methyl, let's say we have got a carbon which is bonded to a bromine, we have got 3 hydrogens like that. Then I can have also, so this is a methyl group which is bonded to the alkyl. Okay, so I can simply show this, instead of me showing carbon and those 3, I'll just show it like this. We have got a carbon here and then attached a bromine. So this is a methyl group. I can as well show a primary carbon. So let's say we have got a carbon which is bonded to another carbon, and then we have got an halogen there. We know that all these are supposed to be hydrogens, right? So this carbon is called a primary carbon. Why is it primary carbon? Because it's bonded to another one carbon. So I can easily show this as just a carbon, a bond here, and then another carbon here, and then at the end now we have got the Br. I can as well show a secondary carbon. Now a secondary carbon is supposed to have 3 things attached. I mean 2 things. one carbon here, one carbon here, and then this carbon is the one we're saying it's a secondary carbon. Now at the end we have got now a bromine which is attached here. This is a secondary carbon. We can also have a neopentyl where you've got a carbon on the middle but it's bonded to one carbon, two carbons, three carbons, right? We have got this carbon and then now bonded to another carbon. Now this carbon which is here is the one which is bonded to the bromine. And then we can have also a tertiary carbon, a carbon which is directly bonded to three things, and then now it is bonded to a bromine. So by the steric factor, because this bromine has got only one carbon that is hindering it from being attacked. Remember, when we are attacking these in an Sn2 reaction, you attack from the behind. So because there is only one carbon that is hindering the attack of the nucleophile which is coming from the behind, it is more easier to attack. Actually, we want to attack this carbon which contains the bromine, and the only things surrounding are the hydrogens. So it is easy to penetrate the hydrogens and be able to attack this carbon which has the bromine. And so the steric factor for this one is lower. Now if you consider the carbon which is bonded to the bromine in the second one is this one, but it is bonded to another carbon which has got three hydrogen, and actually it also has two hydrogens. So for you to attack from the behind where the bromine is, there is this carbon offering hindrance, and so the steric factor is a bit of higher. Now if we consider this carbon here, okay, it has got this carbon, it has got this carbon which are offering hindrance to the nucleophile which is supposed to attack in the direction that is opposite to this one. So the steric factor is much higher. So if you consider now this carbon, of course it itself it has only two hydrogens, but it has got this big group which has also another carbon there, another carbon here, another carbon here. So the steric factor becomes a bit of high, but it will not be higher in comparison to this one, because here the carbon itself that is supposed to be attacked is the one bonded to these carbons, but here the carbon which is supposed to be attacked is bonded to one carbon, but that carbon is now bonded to other carbons. So the steric factor is a bit of lower, right? Not lower, but it's even much higher in that case, let me say, because this group is much bigger. It has got a lot of carbons which are going to offer hindrance, plus the hydrogens, like that, plus the hydrogens, a lot of them. Even these hydrogens are here. So for you to attack this carbon from the behind like that, there is a lot of hindrance from these other carbons. So the steric factor is higher, and Wes is still in a tertiary carbon. This one, it has got this carbon again, it has hydrogen, this one it has hydrogens, this one has hydrogens. For you to attack from the behind, there is much more hindrance. So because of that, the rate of an Sn2 reaction is fastest for a methyl group, followed by a primary carbon, followed by a secondary carbon, and then a neopentyl, and then the least to react. So it is the least reactive, that is the tertiary carbon. It is the least reactive when we talk about Sn2 reaction, because the steric hindrance is so much high, right? So just the same on the steric hindrance, there are some compounds which are never able to react in Sn2 reactions because the hindrance is just too much high. And those we can talk about are aryls and also vinyls. So when you talk about a vinyl, we are talking about a carbon that has got a double bond. So we can have an halogen attached here. Let me say it's a bromine. Then we can have anything attached. It can be an hydrogen or anything. Okay. So because this bromine here, you see there is more hindrance this side. There is a greater hindrance because of this double bond. So this cannot react in an Sn2 reaction. So this reaction cannot happen. You can't have a nucleophile attacking this carbon. It's not possible in an Sn2 reaction. So apart from this, also aryls. So aryls, these are simply rings, right? So when you have got, let's say, bromine which is attached here on this ring, you want to attack from the behind of the bromine, so this reaction can't also happen. It's not possible. Now what can we say? Is this ring a benzene ring or it is a phenyl? So to identify whether it is benzene or phenyl, you can just look at this. When you have got a 6-membered ring like this one, inside we are going to have alternating double bonds, and then something is attached at this position. This is called a phenyl group. So we can, the other formula we can give, we can just say pH, we put that, we attach something here. This is a phenyl group. The other formula that we can use is C6H5, and then we attach something here. This is a phenyl group. Now when we're talking about a benzene, it is actually a phenyl group plus another functional group, right? A phenyl group plus another functional group, which is a methylene group. So you get to attach another carbon here, and then now to this carbon now you attach a substance. So this is a benzene now. So that is just something that I needed to mention. So these are not able to react in Sn2 reaction. So these are some factors that affect the rate of an Sn2 reaction. Now when you consider just the methyl itself, CH3, if this is bonded to bromine, this is the substrate that is supposed to be attacked by the nucleophile. Now if we remove this bromine, we get to put an oxygen here. Oxygen has got a lone pair of electrons like that. So because of this, this now becomes the nucleophile, because we have got the oxygen with lone pairs of electrons that are able to attack the alkyl group. So this one has become the what? The nucleophile. So this is a methyl and then oxygen. So the name of this one is called a methoxide ion. So a methoxide ion is actually a very strong base, because if I had attached hydrogen here or something, that would be an acid. So if we remove that hydrogen, it's now a base. So it's a strong base. At the same time, it is also a strong nucleophile. The reason is because it is unhindered. You can see it is only bonded to one carbon which has got hydrogen. So the steric hindrance is very small. But if we can consider this one, CH3, CH3, and then you have CO, I've got K. So this compound here, which you call butoxide. So this one, we can actually put a 3 there, and then put CO. Okay, this is a tet butoxide. It's a strong base also. It's a very strong base also, but it is a weak nucleophile. The reason as to why it's a weak nucleophile is because we have got a lot of carbons which are attached to the carbon that has got the oxygen which attacks other groups. So that is why it is a strong base but a weak nucleophile, because of steric hindrance. So another thing that you need to note is that nucleophilicity, okay, nucleophilicity is going to increase with increase in negative charge. So that is when you are comparing water and an hydroxide. An hydroxide is a stronger nucleophile than water because an hydroxide has got a negative charge than water. Now you also can compare electronegativities. When something is less electronegative, it is more a better nucleophile than the one which is more electronegative. For example, iodine is down the periodic table as compared to bromine, and so iodine is a better nucleophile as compared to bromine. That is in a protic solvent, not just a protic solvent but a polar protic solvent like water. What could be the reason as to why this one, which is less electronegative, gets to be a better nucleophile in a polar protic solvent? In a polar protic solvent like water, there is hydrogen bonding. So if this nucleophile is surrounded by water, it forms hydrogen bonds with water, it's going to be weakened. Now because this one forms weaker hydrogen bonds with water, this one is more electronegative. It means it forms stronger hydrogen bonds with water. It means it's prevented from attacking the alkyl halides. So because of that, it tends to become a weaker nucleophile because of electronegativity. That is in a polar protic solvent. But it is going to be different when we are talking about a polar aprotic solvent. So if I put A here, aprotic, In an aprotic solvent, there is no hydrogen bonding. And so, since there is no hydrogen bonding, this one is going to become a beta attacking group. It can do that better. It can actually attack better the alkyl allies because it is more electronegative, right, as compared to this one. So that is in an aprotic solvent. But in a protic solvent, you consider those which are less electronegative. They are going to be the fastest or the better ones you can opt to use. Apart from that, a strong anionic nucleophile always favors Sn2 reactions. So Sn2 reactions are favored by anionic or anionic nucleophiles. So those nucleophiles which are negatively charged are better for an Sn2 reaction, and they should be strong, right? So some things that we are able to talk about now. So for basically for an Sn2 reaction, it gets to work better in a polar aprotic. So this is the environment that favors Sn2 reactions. So it works better in a polar aprotic environment. For example, we can talk about tetrahydrofuran, that is THF, or oxalane, the formula that is CH2 4 with oxygen there. So these are better solvents for us for an Sn2 reaction. Okay, so this one we can give it like that, the formula. Okay, so this is aprotic because you can see this oxygen is not bonded to any hydrogen, and so because it's not bonded to any hydrogen, it can't form hydrogen bonding, so it is aprotic. We can also talk about this one, acetone. Acetone is also polar aprotic, so expect it to be a better solvent in Sn2 reactions because it is not bonded to an hydrogen, right? So the reason as to why that is the case is because these do not form hydrogen bonding with nucleophiles or even with the ions that are getting to be formed. Because if you form hydrogen bonding with a nucleophile, it means that the nucleophile will not be able to attack the what? The alkyl halide. For example, hydroxide. Let's say the hydroxide is surrounded by the acetone. How is it going to be able to attack the alkyl halide? So that slows the rate of the reaction. So that is why you would rather favor. Now, this is aprotic. It can't form hydrogen bonding. I was supposed to mention example of water, which can form hydrogen bonding or surround this one in what we call solvation. So solvation, this compound is going to be surrounded by the polar water molecule. Because of that, it will not be able to attack the substrate. So the rate of the reaction gets to decrease. So the more stable the conjugate base of the leaving group is, the more likely that it will take the electrons from the carbon in the bond. So what you want to have is when the reaction gets to happen, the product which is formed should be stable. So the more stable the conjugate base of the leaving group is, the more likely that it will take the two electrons. For example, when you get to now, how do you talk about stability of those conjugate bases which are formed? I can talk about, let's say, CH3, which is bonded to an iodine, and then I can also talk about, let me talk about CH3, which is, let's say, bonded to a chlorine. Okay, like that. So if this one undergoes as an Sn2 reaction, so which one would we think is going to be better? Okay, which one is going to be better in these two reactions? So when you get to attack this one from the behind like this, what you are going to form is that this is going to be released as the conjugate, because this is the halogen, and whenever you are talking about these Sn2 reactions, this has to be substituted by the nucleophile, right? So this is going to be substituted, and so you are going to have I minus, and then this side you are going to have Cl minus. If you talk on the periodic table, iodine is down, chlorine is much on top. Now chlorine is more electronegative than iodine. right? It's more electronegative than iodine. So when you're talking about electronegativity, when this chlorine bonds to hydrogen, you form hydrogen chloride. This is, or hydrochloric acid. It's a much stronger as it's a weaker acid, let me say. Why is it a weaker acid? Because there is a stronger bond between the hydrogen and the chlorine, and so it's not easy to lose this hydrogen. So the higher the electronegativity, the weaker the acid. So meaning that if you lose this hydrogen, this base which is going to be formed is going to be a very strong base because it's coming from a weak acid, and this is going to be a what? A weak base because it's coming from a stronger acid. So because this is a weak base, what you want to do is when you form a product, the one which is formed, the compound that you are releasing in the reaction to take up the reaction should be more stable. The more stable it becomes, the easier or the more the reaction is going to be favored. So iodine is going to be much favored to be released than chlorine. Why? Is because it's going to be more stable. The reason as to why it is more stable is because it is a weak base as compared to the chlorine. So the more stable the conjugate base or the leaving group is, the more likely it will take the electrons. Right. So that is a point that we should be able to take from here. So just a trend that you are able to notice when you are talking about these. So the nucleophilic strength, this one is going to be stronger than this one, and that is going to be much stronger than the iodine. It's going to be much stronger than the CH3O minus, which is going to be much stronger than the hydroxide, stronger than the chlorine, and stronger than the ammonia, stronger than the CH3, CO2 minus, and then the weakest is water. So from this trend we can see that water is more stable. So because it's more stable, it is more opted to be the leaving group or to leave when the compound is being attacked. But this strength is the nucleophilic strength. So meaning that this is a very better nucleophile in comparison to these others. So if you are talking about the rate, this one and this one attacking the same substance, this one attacking the rate of the reaction is going to be much faster than this one.